Let's try to solve example 2. Okay, again, please read this example statement. Now, let's try to read it together, and I'm gonna again mark important words to explain how to tackle this problem. So now we have an air is compressed by an adiabatic compressor. Okay. Now the inlet condition is 100 kilopascal and 12 degrees Celsius. Or we can change that to absolute temperature, which is to 85 Kelvin. Now, because we are talking about the air, we can assume that as ideal gas, and which is also written here in the assumption. Now, exit pressure is 800 kilopascal. So air is compressed, by running the compressor from 100 kilopascal to 800 kilopascal, like 8 times higher. We don't know the temperature yet though. And steady state, here we go. And the mass flow rate is 0.2 kilogram per second. And another given condition from this statement is the isentropic efficiency of the compressor is 80%. So from these given conditions, now can you calculate the exit temperature of the air and the required power input to the compressor? Now, in order to tackle this problem, I strongly recommend you to review lecture note 18. Okay. This lecture note is about entropy change for ideal gases. And we are going to use what you learned in the lecture note to solve this problem. And what I'm going to do for this example too is I'm going to use two conditions. The first condition I'm going to use is when your ideal gas has variable specific heats. And second case is that when your specific heats can be assumed to be constant. Okay, so now I'm going to do the first thing, then variable specific heats. Okay. Again, your compressor is in steady condition, and we also ignore the kinetic energy and potential energy changes. Okay. Now, let's try to draw TS diagram. Now, because we are dealing with air, which is assumed to be an ideal gas, we basically don't worry about any phase change. So when you deal with this air, we basically don't have to worry about the saturation dome. Okay. So if we try to draw the TS diagram, still we need two constant pressure curves, which should look like that. So that is at P1 or 100 kilopascal. And we have another constant pressure curve, which is P2 at 800 kilopascal. So again, the TS diagram is kind of far away from saturation dome, such that we don't really have any kind of saturation change processes. Then let's say that we have inlet condition at 1. Then if your compressor was an ideal compressor, then your process would have gone up with the vertical direction. So that is to S. But in reality, you have a compressor that has that increases the entropy at the exit. So in that case, we may have end up here. Let's say that is at 2. Okay. Now, the first question is, how we can calculate the temperature at the exit. Okay. Now, because we are dealing with a variable specific case, we have to use a table for an ideal gas. And for an air as an ideal gas, we have to use the table A-17. Now let's try to look at table A-17. If you look at table A-17, then you basically can find out this table which has temperature, enthalpy, reduced pressure, specific internal energy, reduced specific volume, and entropy circle. Okay? That's part of entropy, which is only a function of temperature. Then at 285 Kelvin, now you can find out all values like H values and all other values. Okay? Because we do know how pressure will change from 1 to 2, what we may need at this point is at 285 Kelvin, we need H1, that is 285.14 kilojoule per kilogram, and also we need the reduced pressure at 1, which is at 1.1584. And why do we need this reduced pressure? Because now, if you think about state 2s, the exit point of the ideal compressor first, then that is isentropic, result of isentropic process. So from the lecture note 18, we can find the relation of how pressure would change as a result of isentropic process. So now we have to use P2 over P1 should equal to PR2 over PR1. That is, should be satisfied when your process is isentropic for an ideal gas. Okay. So from this value, we can calculate PR2, the reduced pressure at the exit, because we do know P2 and we do know P1 and we know PR1. So from this relation, our reduced pressure PR2 is 9.2672. Then how can you use this reduced pressure at 2? Now, let's go back to table A-17. Then we just look through this table to find out the range of temperatures where we have reduced pressure in between. So from this table, what you can find out is for the given pressure 2, the calculated pressure 2, reduced pressure of 9.2672, this value is in between 510 and 520 Kelvin. Okay, so now what you have to do is using those values to use interpolations. I hope now you know how to do the interpolation. Then, from the interpolation, we can calculate H2S at 517.05 kilojoule per kilogram. So let's go to the isentropic efficiency of the compressor. Now, the compressor efficiency is defined as H2S minus H1 divided by H2 minus H1. So from this given defined equation, H2 can be calculated by the equation of H1, right? Okay, hold on please. Now H2 is H1 plus H2S minus H1 divided by eta C. We have all these values H1, H2S, and eta C. So using this equation, now we know H2 value, which is 575.03 kilojoule per kilogram. Okay, then let's go back to the table. Again, we have to find out the range of temperatures where we have the value of enthalpy at 575.03 kilojoule per kilogram. So by look through the table, again, we find out that this enthalpy should be in between 560 Kelvin and 570 Kelvin. Now, again, we use the interpolation to find out the temperature at the exit T2. So again, by using interpolation, now T2 can be calculated as 569.5 Kelvin. And based on those values, we can calculate the compressor power that we need to run as m dot H2 minus H1. Again, if you don't know about how we get this equation, so please study lecture note, the previous lecture note. Now we know m dot, we know H2, and we know H1. So we can calculate WC dot as 58.0 kilowatt. Now, what if we use constant specific heat? Okay, so let's assume that I already gave you the constant specific heat at average temperature approximately at 470 Kelvin. Then I gave you, or let me just write it down, the constant CP value, 1.023 kilojoule per kilogram Kelvin, and constant CV at 0.73736 kilojoule per kilogram Kelvin. And from this CP and CV value, you can also calculate K, which is CP over CV. Now that is 1.39. And also for the air, the gas constant is 0.287 kilojoule per kilogram Kelvin. In fact, you can calculate this R from CP minus CV. Now, we still know that the inlet temperature and inlet pressure. Then how about the isentropic process from 1 to 2 to S? So that is isentropic process. So because there is isentropic process of an ideal gas, we can use T1, the relation of temperature and pressure. So now T1 times P1 powered by 1 minus K divided by K should be constant at T2 and P2 1 minus K divided by K. So from this relation, now we can calculate, in the case Ts, right? T to S as T1 times P1 over P2 1 minus K divided by K, or T1 times P2 over P1 K minus 1 divided by K. So now we have all other values that we need to calculate T to S. So from this relation, I can calculate T to S as 510.78 Kelvin. Okay. Now, if you try to use the compressive efficiency, which is again H2S minus H1 divided by H2 minus H1. Now, because we use a constant specifics, H2S minus H1 can be written as Cp T2S minus T1 divided by Cp times T2 minus T1. So Cp can be cancelled. So when we assume the constant specifics, now the isentropic efficiency of the compressor for an ideal gas can be written as only the temperature information. So from this equation now we can calculate T2, which is T1 plus T2S minus T1 divided by compression efficiency, which gives us 567.22 Kelvin. So that is the first answer. And again, the compressor power is m dot H2 minus H1, which is m dot times Cp times T2 minus T1. Now we can calculate that equation. The compressor power is 57.7 kilowatt.